going to continue talking about acids and bases, which we started a long time ago, I know. So I'm going to try and refresh your memory. Um, you should already have most of this stuff written down. Um, so just to refresh, acid-base reactions are what we call proton exchange reactions. That's where one molecule takes H plus, which we call a proton, away from another molecule. The thing that loses H plus is called an acid. The thing that takes away H plus is called a base. And then we have these things we call conjugate pairs. So HCl and Cl minus, that's a conjugate pair. HCl is the acid, Cl minus is a base. Anytime you have something that loses H plus, it becomes its conjugate base, which could then go and take H plus back from something else. So in general, we have these reactions. Our generic acid we'll call HA, and we want to look at how this plays out with specific organic molecules. And the last concept we talked about was how the strength of an acid is how good it is at giving away H plus. So it's a weird concept of strength because normally we think strength is how tightly something is held, but really for an acid, strength is how weakly it holds H plus, how willing it is to give it up. So a stronger acid is one that more of the molecules will actually give up H plus in water. And we said we have this thing called the pKa scale that you can measure it on. And I gave you a list of pKa's of a bunch of organic molecules. So I'd like you to take out that pink sheet if you could, because we're going to look at it a lot. So if the strength of an acid is how good it is at being an acid, so how good it is at giving away H plus, then if we want to look at the other concept, the reverse concept of base strength is how good a molecule is at taking H plus from other molecules. So base strength is a little more intuitive because we think of strength as ability to like hold on to something or go grab something. The strength of a base is really how good it is at going at and ripping H plus away from other molecules. So a really strong base is one that takes H plus away from molecules easily. A really weak base is one that is unlikely to go take H plus away from another molecule. All right. So in other words, it's the likelihood of this reaction. Base the more likely this reaction is, the stronger we would say the base is. So we mentioned you have this thing called conjugate pairs. An acid, when it loses H plus, becomes its conjugate base. There's going to be a very straightforward relationship between the strength of an acid and the strength of its conjugate base. It's pretty intuitive, all right? When we think about a conjugate pair, so when we say the relationship between acid and base strength, really we're talking about for a conjugate pair. HA, and A minus, where HA would be the acid and A minus would be the base. So if you think about any conjugate pair, if HA is really likely to split up and give away H plus, what does that mean about how likely A minus is to go out and steal H plus? If they were really willing to split up, that means A minus doesn't really care if it has H plus or not, and it's going to be less likely to go out and grab it. So another way to say that is the stronger HA is as an acid, the weaker A minus will be as a base. So the logic is this. Stronger acid means it's more likely to give away H plus. If it's more likely to give away H plus, it's less likely to take it back. Something that's really willing to give up H plus is less likely to take it back. So whenever we're talking about base strength, we usually compare it to its conjugate acid. And the stronger the acid, the weaker the conjugate base. So I told you to take out that pink sheet. So on that pink sheet, you've got a list of acids and conjugate bases and pKa's. And just like a sampling of them, you have at the top of the list, you have butane and then this negative ion, and the pK of that was 50. And if you go down the list of ways, somewhere in the middle, you had propanol and its conjugate base, and the pK there was about 16. And further down the list, at the bottom, you had this and this, and its pK was -2. So as you go down, lower pKa values mean these are stronger acids as you go down. So this is increasing acid strength. If you consider the things in that conjugate base column, that means those will get stronger in reverse, going up. So the way we use this list is we use it to decide when reactions are more likely to happen. So if you're dealing with an acid that's toward the bottom of this list, it's very likely that it's going to lose H plus in a reaction. If you're dealing with a base at the top of this list, it's very likely that it's going to take H plus away from something else in a reaction. So that's the way that list works. Things at the bottom, really likely to lose H plus. Things at the top, really likely to take H plus away. So I gave you a list. So you have that to give you a sense of how strong or weak different acids and bases are. But I also want you to develop a little bit of a conceptual understanding of why certain things are more acidic or more basic, why certain molecules would be more willing to gain or lose protons. So I'm going to talk about some of the factors, all right? One factor is electronegativity. So let's think about how the electronegativity of the atom that H is bonded to will affect how likely the reaction is to happen, all right? So if I imagine these 4 acids, in each case you have hydrogen bonded to a different atom. In the first case you have hydrogen bonded to carbon. If a base were to come along and take that hydrogen, it would leave a negative charge on carbon. In the second case, we would leave a negative charge on nitrogen. In the third case, we would leave a negative charge on oxygen. And in the fourth case, we would leave a negative charge on fluorine. So you have the intuition to be able to tell me which of those things is most likely and which of those things is least likely to happen, just based on what you know about stability of molecules. So of those 4 possibilities, which one would you think is most likely to happen and why? Go ahead. All right, the response was the last one, the one where we put a negative charge on fluorine, because negative charges are more stable on more electronegative atoms, right? So going down this list, we would expect these to get more and more likely. All right. Do we have a measurement that could back us up? Well, now we do. You have that list, so we can think about what the pKa values are, because those tell us how likely these are to happen. So look at your pink list. This first molecule, what kind of molecule would that be? That would be an alkane. And an alkane, if you look at the top of the pink sheet, has a pKa of around 50. pKa of 50 means this is very, very unlikely to happen. All right, we go down to the next one. What functional group do you see in the next molecule? And they're all listed there on the pink sheet, so you should be able to find them. I can be patient. It's an amine. Yep. And what's the pKa of an amine? 35. Good. All right. Still not very likely, but more likely than for the alkane. And then if we look at the next one, what functional group do we see there? Go ahead, Livy. Not well. So the response was terminal alkyne. That's the next one on the list, but it's not the next one here on the screen. So what is this one on the screen? Check. This is an alcohol with a pKa of about 16. Then the last one isn't even listed because it's not an organic molecule, so I didn't put it on the list for you, but that has a pKa of around 4. So as we go down, these become more and more likely to happen, meaning these acids become stronger and stronger the more electronegative the atom is that hydrogen is bonded to. So the trend that we see when hydrogen is bonded to a more electronegative atom, that makes a stronger acid. We can say the reverse for bases, because as we go up this list, we would make stronger and stronger bases. So when there's a lone pair on a less electronegative atom, that makes it a stronger base. So with electronegativity, the trend makes sense. It's exactly what you would have predicted just based on what you know about stability of formal charges. There are questions before we look at the next factor? All right. Let's compare then if I had these two molecules and apply the same logic. So the first one we already saw on the previous slide. We take H plus away from an alcohol, we're left with this negative charge on oxygen. If I take an H plus away from this second molecule, which is called a thiol, then I'm left with a negative charge on sulfur. So based on your chemical intuition, what do you expect? Which of these is more likely? Leave a negative charge on oxygen, leave a negative charge on sulfur. Oxygen. Oxygen's a lot more electronegative than sulfur. So your intuition says the first one should be more likely. So the first one should have a lower pKa value because it's more likely to lose H+. Take a look at your pink sheet. pKa value for an alcohol, we already said was about 16. pKa value for a thiol is about 12. So this doesn't follow the expected electronegativity trend, right? So as chemists, as scientists in general, you get data that doesn't follow your previous hypothesis. What do you have to do? Change your hypothesis, come up with a new explanation. So that electronegativity explanation, that seems to hold when we were comparing carbon, nitrogen, oxygen, fluorine, all of which are in the same row of the periodic table. But now we're comparing between two rows of the periodic table. So if we're comparing between two rows, what's different about sulfur compared to oxygen? What's different when you go down a row in the periodic table? There's another energy level that's filled, right? So sulfur's valence level is level 3, oxygen's is level 2. What does that mean about the? And there's a clue at the top. What does that mean about the size of the atoms? All right. Higher level valence electrons means that they are further from the nucleus, so the atom is bigger. So why would the size of the atom matter? Well, think about hydrogen. How big is a hydrogen atom? So tiny. So tiny. Uh, so when you think about bigger atoms trying to bond with hydrogen, this is one where I always go to the analogy of trying to hold a baby's hand. And imagine someone with really, really big hands trying to hold a baby's hand. It's like the baby's hand can like slip through the cracks in the big hand. Bigger atoms have a harder time holding on to hydrogen. They don't bond as effectively. Their orbitals don't overlap with the hydrogen orbital as effectively. And so what we're seeing here, the trend, is that the bigger the atom that hydrogen is bonded to, the stronger the acid. So bigger atom being one further down the periodic table. And if we want to say the opposite statement for bases, we would say smaller atoms with lone pairs tend to be stronger bases. All right, so we've talked about two things that affect acid strength. And we can use that to explain a lot of what we see in the chart, right? The electronegativity can explain the differences between carbon and nitrogen and oxygen and fluorine, and the size thing can explain the difference between this alcohol and a thiol. And if you look at your strong acids, even in between HCl and HBr and HI, we see as you go down the periodic table, the acids get a little bit stronger. Those are on the back of your pink sheet. All right, other factors that are in your pink sheet. On the front, you may notice we have a thing called an amine and a thing that we call a protonated amine. In both cases, hydrogen's bonded to nitrogen. But what's the difference between an amine and a protonated amine? Protonated amine has a positive charge, right? So if we consider comparing an amine to a protonated amine, and where does that name come from, protonated amine? Well, it's an amine with a proton added to it, hence protonated. Let's see if our intuition holds in this case. When do you think it's going to be easier to remove H plus from something that has a positive charge or something that doesn't? Or another way to frame the question is, which is going to be more likely to give away H plus, something that has a positive charge or doesn't? Yeah, the one with the positive charge should be more willing to give up H plus, because then it's getting rid of its positive charge. If we look at the pKa values, does that hold true? pKa of an amine we already saw was 35. pKa of a protonated amine, 9. So that means protonated amine is much more likely to give up the H plus. You can see the same thing with an alcohol and a protonated alcohol on that sheet. Alcohol pK of 16, protonated alcohol -2. So there's a big difference adding that positive charge. Charges matter a lot. They make a big difference. So the trend here, plus charges make acids stronger. If you wanted to say a similar statement for bases, what would you say? What's going to make a base stronger? A negative charge, yeah. All right, so the question is, I understand why the negative charge would make a base stronger, because a negative thing is going to be more attracted to a positive thing, more attracted to H plus. Why would a positive charge make an acid stronger? Well, if you think about it, when something already has a positive charge, usually taking that charge away is going to make it more stable. So if something can go from positive to neutral, that's usually going to be favorable, because we know that neutral molecules are usually more stable than charged molecules. Another way to think of it is the positively charged molecule has an extra positive charge that's sort of like repelling the proton. And so for something else to swoop in and take it away, more likely to happen. All right, I'm gonna call it there for today. There are 2 more factors that we'll talk about next time. We've got a couple more weeks where we'll do this next Monday and the Monday after that, and then we'll be done with acids and bases, and you'll know everything you need to know for organic chemistry in terms of acids and bases. Questions before we quit?